Okay, so let's solve this question about rotational motion together. Um, for me, whenever I try to solve this rotational motion, I will try to link it with the translational motions that we learned before from topic A1 and A2 about the translational motion. And it's kind of like very similar to the A4 for the rotational motion. Yes, so for translational motion, the very common equation we use is like for the Newton's second law, right? Vector F equals to m times vector A. And for the rotational motion, um, instead of like measure the force as a factor that can change the translational motion here, we will study the effect in rotation, so like the rotational effect, which is measured by another quantity as the torque, and it is defined as r times with f, with r as like the radius. So like for example, if you got any irregular shape that is rotating, you apply a force at somewhere here. Okay, so then you got this is the applied point as the A, which is the applied point, which means that's where the force is like acting on the object and make it rotate. So if it rotates, it should like rotating around a point, right? We call this one as the pivot point. And then if you draw a vector from the pivot point to that applied point, then you got that's the radius r. Okay, so basically torque itself is a cross product of vector r cross with vector f. If you want to discuss more about the definition of this one and what does it mean, we can talk in another video, okay? But here I just want to remind a little bit about the definitions of the torque. And what I want to highlight here is the similarity between translational motion and rotational motion. So in translational motion, we use mass as a quantity to measure the inertia. It means the tendency to resist the change of the object in translational motion. In rotational motion, we use something similar, also have to do with mass, but that is named the moment of inertia I. Okay, moment of inertia I here. And the definition of this one is like it the sum, like the total sum of every little mass time width that r square. So that r is also like the radius from, like you can imagine a rotating object is a collection of all little things like this, and this little particle here have a little mass. So if you can determine the pivot point, you can see that at this point, at this mass here, little m's here, you have a vector r, a radius r, then you have another m here, let's say that this is m2, then you have also another radius r. Okay, so then you got all the collection of the little m here, and then you times with the square of the radius here all together, that will represent for the moment of inertia, which also means like the inertia in rotational motion. Okay, so that's why for this one the mass is kind of similar to the I in rotational motion. And in rotational motion, we need to measure like how does this rotate, right? And when it's rotating, there should be some change in the angle that it can rotate, it can swap an angle while it's rotating. So we also use another different quantity, not just the acceleration. This is the linear acceleration in one direction, and now it's rotating. So we use another quantity which is named angular acceleration. Why I want to highlight this one, because I think that you kind of used to the A1 and A2. So if you can link with A4 based on, sorry, this is A4, based on your foundation on A1 and A2, that should be much better. Okay, so the alpha here itself is also a vector quantity as well. Okay, so let's move on here, because here they want to ask for the change in angular momentum. Okay, so now we can see that momentum. In translational motion, we know that the momentum is symbolized by BP, which equals as a vector itself equals to mass times with the v. Why? Because this one can be seen as like an inertia in motion. Okay, so this is also mean like if something travel at really high speed and it's also like really great mass, it's not very easy to change it state of motion, right? So this one measure the inertia of something in motion. Okay, and here for the angular momentum, you see, it's also have to do with the angle because it's rotating, some angle being swept. So this one will be the L as the angular momentum. This is the angular momentum, which is defined by, you see again, this is the mass. So this one should be the I, okay? Similarity. And this one, instead of like the velocity, as the linear velocity, we have another one named like omega. And this one is the angular velocity, okay? It's just like how the angle being swept over a unit of time, okay? And now we're talking about the change. If you remember, the change in momentum here actually will be the same mass, right? Mass doesn't change. An object doesn't lose any part in its motion. It just have a change in the velocity. So this is the change in angular momentum. And if you can see that if we multiply both sides with the delta t, no, we divide both sides. Let's divide it. We divide both sides with delta t. You got this one m. This one like delta v over delta t. Okay, you see something similar here, right? You see the rate of change of velocity over time, right? So this one actually is like a. So this one turns out to be the f, right? That's why we have another quantity that mentioned like if we multiply both sides with delta t again, then you got the change in momentum equals to f times what t, right? F is a vector. And this quantity we call it like the impulse, which measure like how much a change in the momentum, right? So let's see how it's similar. Here delta p will be delta L, right? And what if it is the mass, then it should be the I. If it is the V, then it should be the delta omega. Okay, and then this one also equals, so this is the F, this should be the torque, right? As a vector, and this is the delta T. Okay, so you can also see that this thing, the change in angular momentum will equal to this one. Make sense? Okay, so now they ask us to find this. They give us the I already and the alpha already. Oh, so see the I and the alpha. So actually this is the torque. So basically we got delta L equals to I times alpha times with delta T. Okay, so that's the change in the angular momentum. So in this case, the system is rotating from rest, so the initial angular speed or velocity should be 0, right? And after how many period? It's a 4 complete rotation, right? So it should reach to a new angular velocity. So how can we find this? Basically, it mentioned about the 4 complete rotation here, right? So for this equation, we got the I already is a constant mentioned in here. The alpha is a constant itself as well. So alpha somewhere here as well. So we just need to find the t. So what is the t here? It's just 4 period, right? Because the time it takes to complete one rotation is 1 period. If it's 4, then it should be 4. So periods usually symbolized as t. So you got delta L equals to I alpha and 4t. Okay, but this is the thing. How can we do this, right? They don't have anything like to do with the t here, so we need to work. We need to figure it out. Okay, so again, angular momentum. So I'm thinking of something maybe we can try to link between these because it's actually also the I delta t, delta omega is the angular velocity, And we actually have something to do with this one. We can either use this one, but we kind of get stuck at the period, right? So we can just go back to this equation. We have these two to choose, right? So in order to find the omega, do you think we can find the omega? Omega final equals to omega initial plus alpha t, right? Initial just like 0. So this one just equals to alpha times 4t. And t itself is what? It's actually 2 pi over omega. Okay? And omega itself here is also the change. Okay. So it's kind of like the period. It's not a constant, you know? It is not a constant. Why? Because you can see that over time, you got the omega changing, right? It becomes faster. So if it becomes faster, or actually in this case it's from rest, and then we just got a constant here. It doesn't mention if it's increasing or if it's like decreasing. We just know it's some constant. So we don't know. We cannot apply this one. This one is just for an instantaneous, at an instant. So it seems that this one doesn't work as well. So what kind of equation that can helpful here? If you remember, there's also another equation that t final minus t initial square equals to 2 alpha theta. This is the magic one, right? Because basically if we want to find a change in angular momentum, we need to know the change in the angular speed, angular velocity here. And that what we can find, because this one actually just like this one itself equals to this one minus this one. So if we know this one is 0 already, so if we can find the final one, we can figure it out. So basically this one is the final square. This one is just on 0. Then 2 alpha stay constant. After 4 complete rotation, how much is the angle it can rotate? Let's say this is the point. 1 complete 2 pi, 2 complete 4 pi, 3 complete 6 pi, and 4 complete will be 8 pi, right? So that should be 8 pi. Oh, so now you can find the W final is a 2 alpha A pi, which equal to 16 pi r. This is the square. If we want to find, we need to square root it. So that should be 16, this one, and it equals to 4 square root of alpha and pi. This is the W, the omega final. So if you plug this one back into this one times with the I, okay, we just times the I here, then this is the answer, right? So that's the B. Okay, so basically for this one conclusion, we use this equation. The equation for this one, let me use the red color then, is delta L equals to I delta the omega, and this one is like I final, right? Because initially this one just like 0. And in order to find the final, we use this equation, the equation that independent of time. So I really like this equation. It's always like one of the most productive one for me to apply in any case to do with rotational motion. So I guess this is pretty a long video, but I hope that it helps you to see that at first we don't know the way. So it either from the definition, it's either that we try and then we see that this one doesn't work because the omega here isn't a constant. We cannot use this one, right? So that's why we need to use this one. Okay, please let me know if you have any question. Thank you.